We have three algorithms to cover today. The continuation of the median finding algorithm from Thursday, a new algorithm called Arbitrage, which should help you on your homework this week, and finally the fast Fourier transform, pinnacle of achievement in numerical computation in the 1960s, enabled tons of applications, also divide and conquer. So let's start with our median algorithm. One clarification right before I start. The left nifty problem, I wanted to go over a slightly larger example just to make sure everybody is aware of that definition of that left nifty. The example in the homework was only for 4 buildings. So the left nifty number, right, this is the number of times that a building is taller than one of its left neighbors. So in this example, this building is taller than none of its left neighbors, so it's going to contribute 0 to this left niftiness. This building is taller than this left neighbor, so it's going to contribute 1. This one will also contribute 1 because it's taller than this one. This building right here, it will contribute 3. This one will be 4. This one will be 3, 2, and 1, 2, 3, 4, 5, 5. So the total left niftiness for this would be 1, 2, 5, 9, 12, 14, 19. Now the way I computed it just right now was an n-squared algorithm, right? I took a building and then inspected everything before it and counted how many times it was taller. So the way I did it was n-squared. The problem asks for a solution that is n log n, which you can do with divide and conquer. Any questions? All right. Median. Remember, the median is, of course, the element where if you were to sort this array, it's the middle element of that, meaning that half the elements in the list are greater and half the elements are less. Now, we discovered that actually to compute the median, or in particular to compute any ith element, to compute the 7th element of the list or the 9th element or the 15th element, you didn't have to sort the list. You could actually do it slightly more efficiently by semi-sorting it. And our approach was something like follows. First, we covered the idea of partitioning an array. So we're just going to pick some random element of this array and then organize the array so that every element of the array that's larger is going to be on the right and every element that's smaller is going to be on the left. Not in sorted order, just on the left. And we discovered that a way that if you had an element that could partition, a way to actually handle the computation of median or selection in general could be as follows. So of course you handle the base case, and then if you're not in the base case, you partition the array along some element p, which say suppose you pick the first element of the array. And now if you're looking for rank I, and p happens to be that rank I, you can go ahead and just return it. That's a lucky case. Otherwise, you're going to recurse, and you're either going to go to this side of the array or that side of the array, depending on whether the position that you're after is either greater than p or less than p. Does that part of the algorithm make sense, what you're doing? It's very similar to merge sort, except you're only going to take one of these branches. You're not going to recurse in both ways. You know that you're after the 17th element, so if you partitioned and the partitioned element was 30, then you know that your answer is in this half of the input, and so you only need to look in that half of the input. And since each of these partition elements, since each of these arrays are some roughly 1/2 of the input, that means that at each recursive call, you're dividing the input by 2, and so you're hoping for a recurrence that is something like this. And that, by a master's method, is going to solve to order n. What was the problem with this approach? The major problem with this was the worst case situation when you're continually unlucky and you always partition in a way that only puts a few elements to the left and everything to the right. For example, if the input was automatically already sorted and you just picked the first element and partitioned and then picked the second element and partitioned and so forth, you would fall into this unlucky situation. So this situation where you just encounter input that gets you in the worst case, it's not as uncommon as it might seem. Now, one standard approach to this is to randomize your input. So first randomly permute it, and then take the first element and partition. And generally, if you analyze that randomized algorithm, you can solve this also in order n. So if you randomly pick a partition element, chances are likely that you're going to pick one element that will partition well. And we'll analyze that. That'll be lecture 27 of this course, how to analyze randomized algorithms like that. But today we want to focus on a deterministic solution to this, and we want to reinforce our notion of divide and conquer. And this is an example, a classic example of divide and conquer that takes this technique up one level. So we've determined that the problem is that we need to find a good partition, right? Oh, so just to continue this last thought, right? When this partition fails, when it fails to split properly, then the recurrence, then the running time follows this right here, right? You spend O of n partitioning, and the size of the recursive half of the array that you look into is essentially Tn minus 1. And in homework last class, you also did a situation where this was something like T of n minus 3. It didn't really matter whether it was minus 3 or minus 5 or minus 7. If it's n minus some constant, then this recurrence is going to solve to theta n squared. Everybody remember that from homework? Okay, so what do we need? We need to find a good partition element. And what do we mean by a good partition element? Actually, it's going to suffice. This one should find an element. It's neither tall, nor short, skinny, nor fat, day, nor night, morning, nor evening. We should find an element that has 30% of the array, so at least 30% of the array on the left, i.e. smaller, and 30% of the array on the right, or larger. In other words, we're looking for an array that's an element that's between the 30th and 70th percentiles. If we can find such an element, then our recurrence will actually become just like the one we had before, and it'll solve to O of n. So how can we find a partition element that satisfies this property? And the solution is bootstrapping. So we are going to use the same techniques that we currently have to find an element that satisfies this property. And what techniques do we have so far? The only code that I've written so far in lecture is for select. So we're going to do something with our array and with select in order to find an element, a partition element. Once we find that partition element, we can go back to the main task of selecting the ith element. Okay? So here's how we're going to do it. What's great about this, I'm going to explain the algorithm, and then after I explain it, we're actually going to find the median person in this class, hopefully. We can implement this algorithm in a way that will help you remember it, and then I'll also know, I know the youngest person is Marissa here, so I'd like to now find the person that's smack dab in the middle. All right, so pay attention to how this algorithm works. Partition. Our goal, again, is to find an element in the 30th to 70th percentiles. And here is how we're going to do it. We take our input array, n elements right here, and we break that array into groups of 5. Now, within each of these groups of 5, what we're going to do, with 5 elements, it's easy to find the median element. You just, either you can sort or you can just, brute force it, figure out how many elements. Sorting is easy enough. So you're going to identify the median element in each of these. So let's say this was the median here, this was the median, this was the median, and this was the median. I believe I have a better version of this. The handout today, does everybody have one? You can follow along and draw this partition aspect of it. It gets a little bit tricky. So you can follow along and copy that on one side of this. So the first step was to divide the array into groups of 5 elements and compute the median of each group. That's in blue. Now the next step is that we gather all of the medians. So here I've done this so far. Question: how many medians are there? How big will this list be? N over 5, yes. Now notice that there were 2 elements left over right here. There could be one leftover group. In that case, I'm just going to take the median of that group as well. And so we'll have n over 5 elements right here. And now here's the trick. Use select. So now we have a smaller list of size n over 5. What we're going to do is now call select of n over 10, right, which is n over 5 over 2, on this blue array. So that is going to return the median of medians. Question? Why is it n over 10? So how big is the blue list? Okay. And so what's going to be the middle element of that list of n over 5? N over 10. Right, yeah. So this right here is the I, right? The element I want to select. I want to select the middle element of this list of size n over 5. I want to this, of course, is not sorted, but I essentially want the median of that blue list. That is going to be the n over 10th position in this list of size n over 5. That is an excellent homework question. So it will work if you split into groups of 6 or 7 or 8 or 9. It won't work if you split into groups of 3. And in fact, we will investigate of why that doesn't work in a homework assignment, along with this three-dimensional problem. I remember, don't... Okay, so what is so special about the median of medians? First, everybody understand what we're doing. What is so special about the median of medians? Okay. Before we get to the speciality of this thing, let's just do a quick analysis of the running time of this approach. So if we're trying to find a partition element and our input is of size n, then the running time of this right here is going to take theta n, right? This step right here, finding the median of each small list. Well, we have n over 5 lists, and we'll take approximately 14 comparisons to find the median of each small list. And so this will also be theta n. Gathering all of the medians, we can do that in order theta n. What about this call right here? How long will that step take? What do we use to represent the running time of an algorithm? A function, right? So what is the function that represents the running time of median, of select? What function have we been using? For example, here, t of n, yeah. So notice that partition is going to be something that's called within. It's going to be called from within select. Select will call partition. Partition will call select. We'll call partition. It'll be like a Viennese waltz. And so we're going to use a variable right here to represent the running time that this step will take. This step is going to call the select algorithm that we're currently writing, except all we know is that it's calling it on an input that is of size n over 5. And finally, returning the result will obviously take theta 1 step time. So the running time of p of n is basically going to be t of n over 5 plus theta n. This formula, put a box around. We'll use it in 2 or 3 more slides. Okay. Why are we doing this median of medians business? This is the really clever aspect of this algorithm. What property does this median of medians have? Here's how I'm going to demonstrate it to you. Let's write each of these arrays. Let's just put them vertically, like this, where this one was the blue one. So let's take each of these arrays and just write them like this. And this is a thought experiment. So this matrix is just a rewriting of the input. And moreover, it's going to be in sorted order. We're going to sort these in order of these blue medians. Okay? So let's imagine that this right here was actually the median of medians. Okay? And we have the relationship that they're ordered like this. This picture is drawn such that this was the median of medians that we're eventually going to return, and the picture is drawn such that the columns are sorted by the blue elements. Question? Okay. All right. So I'll repeat the question. I believe you asked, why was, on this slide, why was this line right here t of n over 5? No. Why was this? Okay, good. Good question. So there are n over 5 small lists. Agree? Finding median of each small list takes constant time. Takes like, if you have a list of 5 elements, to find the middle guy takes 14 comparisons, let's say. So then the overall time for this step is going to be, for n over 5 of the lists, I'm going to do some constant time to find the first blue guy, constant time to find the second blue guy, constant time to find the third blue guy, etc. So overall in that step, I'm going to spend theta n time. Does that make sense? Good question. So here is where we are. In fact, I'm going to switch to a bigger example, which is the other side of your sheet. Now, in our mental picture of this array, right, this array is equivalent to the input. But it is our mental experiment. Not only are we going to sort these elements this way, let's go ahead and sort them this way as well. Okay? So they're sorted in this order, and they're sorted in this order. Does that make sense? Each of the columns is sorted going from top to bottom. Each of these columns is sorted by this middle blue element. So what I want to do is argue about the size of this set right here. Let's reason about the size of this set. Notice this set is the set of elements in the input that are smaller than our median of medians. Yeah? This set smaller than our set of median medians. Oh, yes, of course. It's not a complete set. There could be, as you said, there could be more elements that are smaller, but at least we know that these are smaller. We're going to make a lower bound that says this box right here is at least 30% of the input, and then you might be able to predict the other argument, which is we want to make the argument that this box right here is also at least 30%. So if we know that at least 30% are bigger than me and at least 30% are smaller than me, I'm in the right situation to be a good partition element. Question?
So talk about actually sorting those columns and sorting that blue row. Are we really sorting, or are we just saying the elements that are less than the blue are above and the elements that are more are below, and then same thing left to right on the blue, right? It's not actually sorted, it's just less than on one side and greater than on the other.
Yes. So let me reiterate. In our algorithm, we are not forming this matrix. This is just a picture, a mental picture. It's an experiment for reasoning about the median of medians. And yes, we're only sorting the elements along each column, and then we're sorting each of the columns by their blue thing. So it's not a complete ordering as it is. All we want to do is argue about the size of these two regions. Question in the back? All right. So the first calculation I want you to compute. How many of these blue elements will there be in this blue set? Spend 2 minutes with your neighbor and come up with the number. How many of these blue elements are there? All right. So the first question to resolve this, how many columns? How many columns did we have? We had this many columns, right? Because we divided our input n into groups of 5, and so they're n over 5 ceiling columns. We know that our median of medians is the middle column, and so there are going to be at least this many on the left. Let me write that. Now, let's discount this column, the first column, because it could be an incomplete column, and let's discount the last column because it's not going to be a complete column either because of this partition, this element right here. So I'm going to subtract off 2 to basically discard the first and last. For the remaining columns, how many elements can I now argue are going to be less than red star? Each of the remaining columns has
5 elements, but 3 of them are necessarily less than.
3 of them are necessarily less than star. Okay? So this is how many elements must be in this set right here. Question? Where did I get the 3? Well, so since I've discarded this set right here and this column right here, every other column is going to have blue plus 2 of its buddies. That's 3. So every other column has 3 elements that is necessarily less than red star. I see a puzzled look. Ask me a question. Where did it stop making sense? Where are the 3 buddies? Okay. Overall, we're trying to compute the number of elements that are less than this star element. So we know that this blue element is less than, this blue element is less than, and this blue element is less than. Now, we're going to ignore this first column and this last column, but for every other column, since this blue element is less than star, and since the blue element has been sorted, right, from bottom to top, right, this element is going to be less than blue, and this element will be less than blue. So we know for this many columns, 1/2 times n over 5 minus 2, because we discarded the first and the last. For this many columns, each of those columns will have the blue element, and the element above it, and the element above that one. It'll have 3 elements that will be less than star. Question in the back. We can generalize this. You can tune that parameter and make it slightly more efficient. Any constant above 5 will probably work. Question?
Is it n over 5 in this example if you're splitting it into segments and columns? Or would it be a group of 5?
Yeah, you always make groups of 5. So if you have 100 people and you put them into groups of 5, you're going to have 100 over 5 groups. Question?
So that whole expression is the total amount of elements that are less than.
Yes. That expression is going to be the number of elements we can guarantee to be less than blue star. Yeah, in fact, I'm going to say that although in this slide I wrote ceiling, I believe we can also take this to be floor, ceiling as well. Why is that? This is just a small point, really doesn't matter, but the point is we're going to include the column with the star since we're going to exclude it here. So don't get too caught up with that detail. This is the main point I want to argue, which is that 1/2 of n over 5 is n over 10 minus 2. So if you multiply all of this out, essentially you get that this set right here must be at least 30% of the array. So we know that at least this many people have to be less. So there are at most this many numbers that are larger. There are at most this many numbers that are larger than star. Question? We picked 5, which led us to 30. If we would have picked 7, right, then instead of this number being 3, it would have been 4. And so we would have gotten roughly 40%. The 30%, all we needed was some constant fraction, which 30% comes out to be. And to get 30%, we had to pick the number 5. Question? The thing is, k has to be a constant, because otherwise, that step of breaking the list into n over k chunks, if k is not a constant, then it's not going to be a constant number of operations and so forth. So, all right. So similarly, we're going to argue that this set right here is at least 3n over 10 minus 6. And so, at most, 7n over 10 plus 6 elements are larger. Smaller. So armed with this fact, we can now go back to the analysis of our recurrence right here. Right over there. Actually, I believe it'll be in pictures. What we just computed helps us argue that if we were to partition with this red star, then we know that the size of this array is at most this, and the size of this array is at most this. Now, obviously, they both can't be that size because that would be larger than n, but we know that both ends of this are upper bounded by roughly 70% of the array. Everybody follow that step? So then we are ready to specify our algorithm. So we're basically going to handle the base case. And if not the base case, then we're going to use partition, find partition. And then we are going to partition A using P. And if index I is equal to the index of P, return P, else if I is greater than P, then select. So just like the algorithm we had before, the only difference is that we called this function right here. So now let's write a full recurrence. Let's analyze the running time of this algorithm. So we use T of n to reflect the running time of select. And so, of course, this step right here is going to take time P of n, right? And that was equal to, anybody remember? Perfect. This step, partition, will take theta n. This step, of course, will take constant time. What about this call right here? In fact, what about these two lines? What can we say about the running time of these two lines? Perfect. At most, this is going to be t of 7n over 10 plus 6. All right. So let's write out the full recurrence here. So we know that T of n is going to be T of n over 5 plus T of... Now, there was a homework problem that was very similar, but it had different constants in this. But the same technique for that homework problem will apply here, and by a guess and check method, you'll be able to show that this also solves to theta n. Questions? Why isn't this? Yeah, this is a theta n, and it'll incorporate all of these right here, if you like. You can move the constants inside the theta n always. Question in the back? There's no constant in that. We know that our element is somewhere between. Your question was, we're ignoring a constant. We're not ignoring a constant. We've argued that at most the number of elements that are larger is 7n over 10 plus 6, and that's the same number that are smaller. So we know that in this line, in these last two lines, we know that only one of those lines will execute. It's an if then else. And each of them is going to be running on an input that's at most roughly 70% of the initial input. Question? Oh, for the plus 6. So that's right. The base case, I haven't specified exactly how small the base case has to be here. When you were to implement this algorithm, certainly if you had less than 5, if you had 5 elements, it would kind of not make sense, right? You'd kind of, so at some point you just have to use a brute force approach and solve base cases essentially in another way. I haven't specified that, and this analysis also makes assumptions about how big the input would be. You'd have to work those details out. But for very large inputs, this is the technique. All right, shall we burn a little energy and try this? For those of you that participated in my folly, feel free to... Okay. That was an attempt to do that sort of learning by physical activity. I hope it sort of created some memory so that you'll remember this approach. All right, what's really great is this is the first example of a recursion where it's two functions. Select calls partition, which calls select, which calls partition, and then recurses all the way back up, and then recurses on select again. All right, so it's a very intricate type of recursion. All you need to do understand, though, is these 6 lines of code. You don't need to keep the head of how the whole picture of how the recursion works. You don't need to keep in your head. You just need to understand these general steps. All right? Questions? I want to cover this next problem, arbitrage, because it'll give you some hints about some of the homework problems. So here is the problem. You are a stock trader, and there is some stock which fluctuates like this. Of course, then it's very easy, in hindsight, to have said, I wish I would have bought the stock on this date and sold on this date. I would have made so much money. There might be other stocks which do like this. So you know that if certainly you bought it here and you sold it here, you would not be in a good situation. But even just because the general trend of this stock is that it's going down, doesn't mean that there wasn't an opportunity to make money, because you could have purchased right here and sold right here and still been in a good situation. All right? So even with a stock like this, which I believe was AIG, you can still make money on these type of movements, right? And in fact, this is kind of what some hedge funds do. No matter whether the stock is going up or down or not doing anything at all, because of some statistical motion of that stock, the hedge fund is still making a little bit of money. It's buying and selling or selling and buying and so forth. So the question that we're going to pose today is, suppose you are a hedge fund trader, which I'm sure some of you will become, and you're given an array of n numbers. They correspond to the stock prices for some particular stock. Okay, so closing tickers, let's say. And your goal is to be, in hindsight, what were the days that I should have bought and sold to make the most money? So output a pair of days, I comma j, such that we're only talking about going long. So I has to be less than j. So you bought it on day I, you sold it on day j, and you're trying to maximize, yeah? This is the problem. Graphically, you're trying to find the day that you should have bought and the day you should have sold to make the most money. Formally, you're looking for a pair of days I and j such that I is less than j, and this is maximized. Okay, so clearly you can solve this in order n squared. For each day, you can basically find what was the greatest day on the other side and compare the difference, and then just pick the max among that. So clearly there's an n squared solution. But we obviously want to do better than that. And so, what will we do? Divide and conquer. What will we do? So you find the minimum, you find the middle, and then what? Yes. Yes. And the guiding principle is that both of them were divide and conquers. Yes. But what could happen? So the analysis I believe that you're trying to lead to is that, look, the way you're going to make your money is one of two cases. Either the buy and sell is completely on the left, the buy and sell date is completely on the right, or you buy on the left and you sell on the right. Those are the three cases. And so we can solve this with with divide and conquer as follows. Let's find the ij. Let's recursively call arbitrage on the first half of the array. Let's call it on the second half of the array. Okay? let's, instead of calling this I and j, let's just call this max L and max R. And now, in order to find a Romeo and Juliet situation, we can, question? Okay, we can sort the left, sort the right, okay? And now, sorry. So the point is, the solution is either going to be entirely on the left, entirely on the right. If it straddles, that means you find the cheapest day to buy on the left and the most expensive day to sell on the right. If the solution is going to straddle, then you know that you had to buy on the left, so you might as well buy at the lowest, and you know you're selling on the right, so you might as well sell at the highest. So in this case, you just find the minimum on the left, find the maximum on the right, and now you're going to return max of max L, max R, and MR minus ML. Now, does everybody agree, here's a typed up version of that this algorithm will solve the problem? Doesn't matter. What you mean in the straddle case? It doesn't matter, as your neighbor is telling you, because you're just going to buy on the left. Doesn't matter. You're only going to look at this min L and max R in the situation that you buy on the left and sell on the right. Everybody agree this is a solution? The thing about this solution is that its running time is going to be this, right? Because each of these steps is going to take theta n time. Each of these steps will take theta n time, and so the running time of this approach is going to be n log n. The point I want to make about this problem is that you can actually do better. One can do better by using one more trick in the book. What created this work right here? These two steps right here, finding the min on the left and the max on the right. How might we be able to? So, good intuition. The thing is, if the array was already sorted, then we could do that, right? But sorting that list is going to take n log n time, which is not going to help us overall. So the point I want to make is, when you encounter a situation like this, you have a solution. In the homework, you'll come to a point where you have a solution that perhaps runs in blah, 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 blah time. And you might want to stop there, but there might be one more step left. So look through your algorithm, find where all the steps are, and try to ask yourself whether these steps are absolutely necessary. In this case, we're going to find a way to remove these two steps and find a solution that has a running time like this. This is our goal. We're going to find that, and then that will give you a solution that's actually linear time. So now, two of you have suggestions on this. That's right. Okay, so the perfect explanation. So I'm just going to repeat it. It says, let's change the problem, make the problem more general, so that in addition to returning the maximum money that you can make, you're also going to return the maximum element in your side of the array. So Arbit will now return, it returns both the ij pair and the max and min elements in the array. So in addition to giving you the pair of days of when to buy and sell, it's also going to give you the max and min on that side of the array. And as you said, in the base case, when you only have one element, that element is both the max, the min, the best day to buy, the best day to sell. So let's see how this algorithm would work out. Okay? So as before, we're now going to say, just like before, we're going to call arbitrage on the left half. We're going to call it on the right half. And now, we'll basically return the max of, just as you suggested. So we handle the base case. We recurse left and right, and in addition to giving us the answer on the left and the answer on the right, it's also going to give us the min and max on the left side. And then we'll just subtract these two, like right here, and compare them with these two. And this will basically give us a solution that runs in exactly the time that we needed to give us a theta n time solution. So the hint is sometimes you have to generalize the problem, perhaps compute some more information so that you can find the answer that you're looking for more efficiently. Questions? So we might as well, good point. So that's right. This return statement also needs to return 3 items. Was that your question, or? Well, that's an interesting point. I guess I haven't thought about that. So yeah, the first day in class was a sort of ill-posed problem, but I guess you can think about that. You're computing slightly more information. It doesn't actually help you go faster in that sense, but it does, essentially you can compute extra information and get it for free at the same running time. But good analogy. Did this make sense? Won't this help you make money? Question. Sure, you can keep the base case. I disagree on if the problem is one, essentially you bought, you sold on the same day, you made 0 money, and that's done, you know? So the base case can be 2 if you like. So in the last minute, I just want to talk about what I'm going to do on Thursday. This fast Fourier transform algorithm, and I want to explain to you what the big idea is. So what the fast Fourier transform does, it just transforms its input. You give it an input, which is a polynomial, and the output of the fast Fourier transform is just going to be the evaluation of this polynomial on n points. Now, we all know from algebra that a polynomial of degree n minus 1, you can equally represent that polynomial as essentially n points on the plane, because you can interpolate between one representation and the other one. The standard way of doing this right here, the standard way of evaluating the polynomial on one point will take n operations. And so if you just do that blindly n times, you'll spend n squared time through this transformation. A divide and conquer approach will help us get this to be n log n. This is a very, very important algorithm, not only for your iPod or for any music type of equalization. This was actually an algorithm that was used for monitoring, for analyzing the seismograph data. So people actually formalized this algorithm, although Gauss knew about it. They formalized it during the 1960s after people were doing nuclear tests. As soon as the Soviet Union and Russia made agreements, Soviet Union and the United States made agreements about controlling the number of nuclear tests they did, they put seismographs in different parts of the world to try to detect when there'd be a nuclear explosion. Analyzing all of that data required a technique like the fast Fourier transform. I'll talk to you on Thursday.